So good morning all. Today we will see what is electric potential. The electric field intensity E due to charge distribution can be computed from Coulomb's law, which we studied earlier. Then if the charge distribution is symmetric, then E can be computed from Gauss law, that also we studied. Now there is another way of computing electric field intensity, and that is from electric field potential, where electric field potential is a scalar quantity. So now let us see a surface. This surface may be a waveguide, and here there are 2 points A and B, and E is the electric field intensity, which is a vector field. Now if you want to move a point charge Q from this point A to B, then the force applied is F is equal to Q into E. And in moving this Q, you have to do a small work, and that small work is given by dW is equal to minus F into dL. That dL is the distance between A and B. Now what I am going to do is I am going to substitute equation 1 in 2. Okay, so I can write dW is equal to minus QE into dL. So dW is a small work done. So if I have to find the total work done in moving the charge Q from A to B, then I have to integrate. So integral dW is equal to integral minus QE dL, and the limit is from A to B, where A is the starting point and B is the ending point of the surface. This one here, the point charge is moving from A to B. So this is the limit of our integral. So I can write W is equal to minus Q integral A to B E dL, where E is electric field intensity, Q is the charge, and W is the total work done. Next we will see what is potential energy. Potential energy is a potential difference between those 2 points, that is A and B. Or in other words, it is a work done per unit charge. That is VAB is equal to W by Q, where VAB is the potential energy between the 2 points A and B. Now I am substituting 4 in 5. So I can write VAB is equal to minus Q integral EDL divided by Q. So Q and Q get cancelled. So I can write VAB is equal to minus integral AB EDL. Then we already studied the expression for electric field intensity as E is equal to 1 by 4 pi epsilon 0 QR square unit vector AR. Okay. Then I am going to substitute this 7 and 6. So when I am substituting 7 and 6, this DL will become DR, because here the term we are using is R, not L. So I am slightly rearranging the expression. VAB is equal to integral A to B 1 by 4 pi epsilon 0 QR square into DR. Then again that is equal to minus integral RA to RB 1 by 4 pi epsilon 0 QR square DR, because here the term we are integrating with respect to DR is R. That is why this A and B represents a point, and RA and RB represents the radius, the distance between those 2 points. So I am writing it as RA and RB. So after integrating and applying the limit, you will get Q by 4 pi epsilon 0 1 by RB minus Q by 4 pi epsilon 0 1 by RA. So this is the expression for your potential. Potential V is in general given by V is equal to Q by 4 pi epsilon 0 into 1 by R. If it is electric field intensity, it is Q by 4 pi epsilon 0 into 1 by R square. The difference is only in the R term. In electric field intensity, in the denominator you will be having R square. Look here. And in vector potential, in potential energy, you will be having what? In the denominator you will be having 1 by R. Now VAB is equal to VB. This first term will give you the potential at B point, and the second term will give you the potential at first point. So that is equal to VB minus VA. So if VBA, if you have to calculate VBA, then your expression will be VA minus VB. Now next we will see the relation between E and V. Before going into the relation between E and V, that is, E is your electric field intensity and V is your potential energy, we have to see a few other formulas. Now you know VAB is equal to minus VBA, because VAB is equal to VB minus VA, and VBV will be equal to VA minus VB. So there is a slight difference in sign only. So VAB is equal to minus VBA. You can write it as VAB plus VBA is equal to 0. Similarly, here we have the expression VAB is equal to integral A to B E dl. So I am rewriting that expression here. VAB is equal to minus integral E dl. Similarly, VBA is also equal to minus integral E dl. Next, what I am going to do is I am going to substitute 2 and 3 in this equation. VAB plus VBA is equal to 0. So finally I will get what? Integral E dl is equal to 0. Okay, and this is Maxwell's second equation in integral form. You have to keep in mind integral E dl is equal to 0 will give you Maxwell's second equation in the integral form. Hope the derivation is clear. Next, I am going to Stokes theorem. We already studied line integral of a vector into dl is equal to surface integral of del cross a vector into ds. Here A is a vector, so I can write integral L A dl is equal to integral S del cross A ds. Now here in this particular section we are dealing with the vector term electric field intensity. So what I am going to do is I am substituting this A as E. So I can write line integral E dl is equal to surface integral del cross E ds. Now here you can see integral E dot dl is equal to 0. So I am going to substitute that value here. So I can write integral surface integral of del cross E ds is equal to 0. So this term is equal to 0. So what I am slightly rewriting the equation, that is integral S del cross E ds is equal to integral S 0 ds. You know this term will be equal to 0. I am just writing this in the integral form in order to cut the integral sign of this right hand side and left hand side, that's all. So finally I can write del cross E is equal to 0, which is our Maxwell's second equation in the differential form. So this is the Maxwell's second equation in integral form, and this is Maxwell's second equation in differential form. Okay, hope it's clear. Then we will go to the next topic. We already know what is V, potential energy V is equal to minus integral E dl. We saw it earlier. Now I am going to differentiate this term. dV is equal to minus A dl. Okay, and we studied in the coordinate system that E can be represented as, if E is a vector, then it can be represented as Ex plus Ay plus Ez. Okay. Similarly, a small length dl or a differential length dl can be represented as dx ax plus dy ay plus dz az in the rectangular system. Next, what I am going to do is I am going to substitute this 8 and 9 in 7. So you can write the expression dv is equal to ex dx ey dy ez dz. This ax is a unit vector, so when you multiply you will get value 1. So dv is equal to ex dx ey dy ez dz with a minus sign, because here It is minus of AdL. Okay. Now Ex can be written as minus of dou V by dou X. So Ex dou V by dou X, then into this dx. Ey dou V by dou Y into this dy. Ez dou V by dou Z into this dz. Okay. Now I am comparing equation 10 and 9, because in equation 10 and 9 the left hand side is equal, so the right hand side will also be equal. So I can write Ex is equal to minus dou V by dou X, Ey is equal to minus dou V by dou Y, and Ez is equal to minus dou V by dou Z. That is written here. Ex is equal to minus dou V by dou X, Ey is equal to minus dou V by dou Y, and Ez is equal to minus dou V by dou Z. And this term is familiar to you, that is dou by dou X represents the gradient, which we studied earlier in this chapter. Dou by dou X represents the gradient of a scalar quantity. Clear? So I can write E is equal to minus del V, where del represents the gradient and V is a potential, which is a scalar quantity. So I can write E is equal to minus of the whole minus of inside the bracket dou by dou X of Vx plus dou by dou Y of Vy plus dou by dou Z of Ez, where V is a scalar quantity. So this is a relation connecting E and V. This also you have to buy on. E is equal to minus del V is a relation connecting electric field intensity and potential. That's all. Thank you.